Full waveform inversion has been successful in building high-resolution velocity models in shallow layers using the diving waves. However, it is difficult in incorporating reflections into full waveform inversion. This is mainly because the background velocity model is not accurate enough to incorporate positions using reflections in time. As a consequence, we get cycle skipping when we start matching the waveforms. So today I will speak about an interesting method to include reflections into full waveform inversion. Earlier, this method was proposed in acoustic isotropic media. In my research, I am planning to implement this in acoustic VTI media. The reflection-based full waveform inversion algorithm was first proposed by Shen Wang in the year 2013, following the work of Sen Xu in the year 2012. The real subsurface Earth can be thought to consist of two parts: the long wavelength part and the short wavelength part. The long wavelength part corresponds to the background model which generates the transmitted energy. The short wavelength part corresponds to the reflectivity model which generates the reflected energy. So here, the long wavelength part is a reference model and the short wavelength part is the perturbation model. So, at each iteration first, the reflectivity model is obtained using the initial background model. For generating the demigrated data affecting the reflected arrivals, we use the obtained image and the initial model. So, the demigrated data is the calculated data here. The data misfit is then calculated between the observed data and the calculated data, which is the demigrated data. The gradient is computed along the wave path of the source of the incident and the reflected wave. And the final step of this approach is the background model update. To illustrate this algorithm, let us take an example of a model with Gaussian anomaly. This was taken from Shen Wang's paper. This model has got a low velocity Gaussian lens in the upper part of the model. The center of the lens has a velocity of 2.25 km per second. There are altogether 191 shots and 251 receivers associated with each shot. And there are two reflectors. The first reflector is sitting at z equal to 8 km and the second reflector has got a certain tipping angle. They started with an initial model that has got homogeneous velocity of 2.5 km per second, which is the velocity of the upper part of the model. After doing the migration, we can note here that at around x equal to 10 km we see artifacts. Well, this is caused due to multipathing, due to the absence of Gaussian anomaly in our initial model, they used. For generating the demigrated data affecting the reflected arrivals, this process, demigration, is an important step. The process demigration can be understood with the help of the two equations shown here. The first equation is the acoustic isotropic wave equation, which has got a delta function as its source. For generating the demigrated data, the secondary sources are generated by multiplying the image with the source waveform. Now these secondary sources from the migrated image, which when propagated in time generates back the receiver data. The observed data was taken for a shot at x equal to 4.5 km. However, in the demigrated data, we can see that there are some extra arrivals at the larger offset at around x equal to 10 km. Again, this is because of the incorrectness of the model, or can say, because of the absence of the Gaussian anomaly in the model which they started. The calculated data is the demigrated data here, and the data misfit, they used a correlation type data misfit function to compute the data misfit between the calculated data and the observed data. The gradient is then computed along the wave path from along the incident and the reflected wave path, that is from the source to the image and then from the image to the receiver. And finally the model is updated. This is the result that they got after three iterations. We can note here that the Gaussian anomaly has surfaced up at x equal to 10 km, and also the two reflectors are visible now. Migration with the updated background velocity could give a coherent seismic image. So if I go back and forth here, you can see that the multipathing has been corrected for. In my research, I am planning to implement their approach in VTI media and estimate the anisotropic parameters. Since I am beginning my research, if any of you are working in this field, then it will be really helpful if I get some input and ideas from you. Thank you.